Hello, I'm Celia Sanchez and I'm a bioprocess engineer. The Raman system is composed of a stainless steel probe, an optical cable, and the analyzer. The system is connected to the computer where the software runs and manages the acquisition of the measurements and allows you to see the result of the measurements in real time. The probe is autoclavable and can be placed directly into the bioreactor or into the container. The measurement area is really close to the probe tip. The probe needs to be immersed into the liquid to enable in situ measurement. Also, Raman spectroscopy is an optical technique which collects lights. It means that it is sensitive to all kinds of light, including the ambient light, such as sunlight or artificial room light. To achieve better and more accurate results, it is highly recommended to have a light-proof environment around the area of the measurement. Raman technology is fully adapted for measurement in aqueous media. It is non-destructive and can provide simultaneous, real-time measurement for several process parameters and quality attributes, including total cell density, variable cell density, glucose, lactate, ammonia, glutamine, amino acids, and proteins. On top of that, the Raman effect is based on the interaction between the light and the molecular bond within a material and on modeling. It means that as soon as the analyte is a molecule in a sufficient concentration and that there is a reference measurement available for model building, it is possible to be measured with Raman. The possibilities are almost infinite. This is an empirical method. Good performances are already demonstrated for the main metabolites such as glucose, lactate, but also for cell densities. Here is a comparison between offline measurement and Raman inline and real-time monitoring. It shows the increase in data points between Raman measurements compared to offline sampling. It also shows the high accuracy obtained with Raman measurement. In addition, with Raman measurement, there is no need of human interaction nor loss of volumes, allowing continuous measurements of the process parameters without loss of products. The Raman PAT platform acquires the spectra and calculates the process parameters, including nutrient concentration. As you can see on the schematic, a feedback control loop can be implemented using a direct OPC UA connectivity between the Raman system and the bioreactor control system. This setup allows you to implement an automated feeding strategy. For example, measurements are taken every 30 minutes and the pump rate can be automatically adjusted to add a complex feed into the bioreactor based on the concentration measured in the vessel. For example, with the feedback control loop, it is possible to maintain the glucose steady for several days during the process. The Raman probe can be used in perfusion cultures. As you can see on the graph, the Raman measurements are really similar to the offline measurements for cell densities from low densities to up to more than 150 million cells per ml. Even with those really high cell densities, the other cell culture parameters are accurately monitored on the whole range, like you can see for antibody productivity, glucose and lactate concentrations.